Hello student, good evening. Today we would be dealing with the concept of linear momentum. In our last lecture, we discussed about the concept of Newton's law of motion. We discussed about Newton's first law, and I gave a brief introduction about the Newton's second law, right? So this lecture will be divided into three segments, right? In the first segment, we would be dealing with the concept of momentum, right? We would be understanding how both mass and velocity are the important parameters for momentum, right? We will try to closely relate this concept with the help of a live examples. Okay. And in the second segment, we will be dealing with the mathematical formulation of Newton's second law, as well as the derivation for the conservation of linear momentum equation, right? And in the third part of this, and in the last part of this segment, we would be dealing with some live numerical problems, okay, based on the concept of conservation of linear momentum, right? So before I start with the concept of linear momentum, right, I would just like to give a brief introduction of what exactly momentum is, and I will try to relate it with some real life examples so that you understand the concept of momentum much better, right? So mathematically, we know that momentum is given mass times velocity, right? This is like the fundamental formula that we use to find out momentum, right? So as we know that velocity is a vector quantity, so momentum is also a vector quantity, right? So we are well aware of the fact, right? But now we know that as per the Newton's first law, right? If a body is acted by unbalanced external force, it gains some velocity, right? Or in other words, we can also say that the body possesses some acceleration, right? But from Newton's second law, we know that it tells us about the dependence of force on acceleration of the body, right? This is what Newton's second law basically tells us, right? So now, before understanding the concept of momentum, let us take two different cases, right? In case one, I would be dealing with the mass, and in the second case, I would be dealing with the concept of I would be dealing with the term velocity, right? So in the first case, suppose there is a table tennis ball, right? And it hits a particular person. So the impact felt by the person in such case will be less. Right? It won't have much impact on a particular person. Whereas on the same hand, like if a cricket leather ball hits a particular person, the impact felt by the person will be much high, right? Right. And why it is so? Like, so as we can, like the reason behind is that we will understand later in the topic. But the thing is, like, it is clear from the observation that one body was having less mass, right? And it did not have any impact on a person. Whereas a cricket leather ball, when it strike a particular person, the impact felt by the person is much more, right? And now let us take the case of second case. So in the second case, suppose there is a car that is parked along the roadside, right? So it will just remain at rest, of course, because like no external force is acting on it. So it will remain at rest only. And like it will not have any impact on the any kind of like surrounding or people present nearby, right? But on the other hand, if you consider a truck, right? Of course, the mass of the truck is much more than of a car. And like even if it is moving at a very small speed of 5 meters per second, it can actually kill a person, right? Okay. So basically, from the two cases that I discussed, it is quite evident that there is a correlation between mass and velocity, right? So actually, in order to quantify both the terms of mass and velocity together, okay, we need a quantity, right, which can actually correlate both mass and velocity of an object. So in order to relate the mass of a body and the velocity possessed by the, like, of course, a moving body, Newton formulated a formula that is written here as m times v, and actually he quantified both the terms of mass and velocity together with a single term that is known as momentum, right? So this is a brief description about like the mathematical formula of m is momentum equals to m times v, mass times velocity, right? So we are well aware of this equation, right? Everybody, like, this is one of the fundamental equation if you have to find the momentum of any particular body. Now let us derive with the help of this momentum principle. Let us first derive the Newton's second law of motion. Okay, and after that, from the Newton's second law of motion, we will derive the Newton's first law of equation as well. And like we will observe like how there is a dependency of both the like the concept of momentum on the Newton's second law of motion as well. And like we will understand like how these terms are closely interrelated to each other, like all the three laws, how they are closely interrelated to each other. So for this, let us consider a following case. Suppose there is a mass, there is a ball of mass m, right? It is moving with initial velocity u, right? And after a small time interval t, the body attains a final velocity of v, right? I would again repeat, consider there is a small ball which is having a mass m. It is moving with initial velocity u and a very small time interval t. Okay, the ball will attain a velocity v, right? So if I want to find out the momentum in this case, the initial momentum, I can write it as m times u, right? And where u is the initial velocity of the body, right? But in the second case, like if I want to find the final velocity, I can represent it as m times v, right? So now if I want to find the net change in momentum, right? Or in other words, I can also say the fractional change in momentum, right? So can I write this as delta p, where delta p is nothing, it is just representing, whereas this del sign is just representing a small change in the quantity, right? So if I want to calculate the change in momentum, can I write like final momentum minus initial momentum, right? So I can also write this as m times v minus m times u, right? So if I take m as common, I can write this as v minus u, right? And that we can equate it at equal to delta p. Now, from the Newton's second law, we know that the rate of change of momentum is directly proportional to the force applied, and the change in momentum takes place in the direction of applied force, right? So this equation is nothing, but it is just a illustration of Newton's second law, right? Fine. So basically what we will do is that we will divide both the equation by time, right? So if we are dividing any particular equation by a small time interval t, so we have to do the same on the right hand side, right? Okay. So this term, like, so what we have done, we have divided by the time on both the sides, right? So we are well aware of this term, right? Can I write this term v minus u by delta t equal to a? Because it can be represented by v minus u by delta t can be represented equal to a. So this equation get reduced to delta p by delta t equals to m times a. Okay. Whereas on the left hand side, from the Newton's second law, this equation, can I write this del p by del t equal to force? Because as per the Newton's second law, the rate of change of momentum is directly proportional to the force applied, right? And it is quite evident from this equation, right? From the Newton's, from this equation that is given in the box, right? F is equals to dp by dt. So what I will do is, I will just replace dp by dt equal to m times a, right? So this is nothing, but it is just an illustration of Newton's second law. And this equation just tells us about the dependence of force on acceleration possessed by the body, right? Okay. And now from this equation, we can also derive Newton's first law. How? I will tell you. See, can I write acceleration as v minus u by t, right? So if I cross multiply the term, I can write it as f times t equals to m into v minus u, right? So as per the Newton's first law, if no force acts on a body, if no force acts on a body, so the left hand side will be equal to 0, right? If no force acts on a body, so this F into T, or the LHS of the left hand side of the equation will become equal to 0, right? For whatever time interval, right? For whatever time interval it is, right? For whatever time interval it is, X, Y, Z, right? If no external force is acting on the body, then the above equation will get reduced to V minus U, right? So we can also write it as V equal to U, right? So this is nothing, it is just an illustration of Newton's first law, right? So the Newton's first law tells us that until and unless any external force is applied on a body, if a body is at rest, it will remain at rest. And if a body is in motion, it will remain in motion until and unless some external force is applied, right? And this can be like, this is easily understood from this equation, right? So till now, what we did that we, from the concept of momentum, right, we derived the Newton's second law of motion, right? And from the Newton's second law of motion, we deduce it to Newton's first law of motion, right? So we can say that there is a close, like these, all these equations are closely interrelated, and all these concepts are also interrelated to each other, right? And it is quite evident. See, from the concept of this momentum principle, we first derived the Newton's second law, and from Newton's second law, we deduce this to Newton's first law, right? So it can be easily understood that the concept of momentum relates the mass and the velocity together, of course, but as you can see that this equation can be used to derive both the laws, both the Newton's law, that is the second law and the first law, right? So this was the brief introduction about what momentum is, right? Momentum is a vector quantity. We all know that. Why? Because since velocity is also a vector quantity, so from this equation, it is quite evident that momentum is also a vector quantity. So if we want to calculate its SI unit, the SI unit of mass is kilogram, and for velocity it is meter per second. So this is its SI unit, right? Okay. Now, in the second case, in the second part of this segment, let us deal with the mathematical formulation of equation for linear momentum, right? So in the, like here you can see a diagram that is drawn on the board. Like, okay, this is a case of ideal collision. Like we would be using the case of ideal collision to like formulate the equation of linear momentum, right? So basically there is three diagrams are drawn. In the first case, that illustrate the condition of the body before collision. Okay. In the second case, it tells us about the point of collision, right? And the third case, it tells us about the condition of the body after collision, right? Okay. So see what this figure is telling us about, that consider there is a ball of mass ma. It is moving with initial velocity ua. The body B, it is having some mass mb, but it is at rest. Okay, for this case to hold true, we are taking into consideration that velocity of body A is greater than velocity of body B. Okay, so what will happen that after a small time interval t, both this body will collide with both the bodies will collide with each other. So for the second case, we can write this as AB. So at the point of collision, there will be, the force will be exerted by body A on body B, which can be represented by FAB. Okay, and equal and opposite force would be exerted by body B on body A. Okay, so this is nothing, it is just an illustration of the Newton's third law, right? To every action, there is an equal and opposite reaction. So in the above case, so in this case, at the point of collision, okay, at the point of collision, the force, the body A will exert a force equal to FAB, and the body B will exert same equal and opposite force, but the direction of two forces will be opposite to each other. It won't be same. Okay, it won't be same. So I can write this equation as, so this equation can be written as, suppose if I want to write, I can write it like this, right? FAB equal to minus FBA. Okay, it is nothing, it is just an illustration of Newton's third law. Okay. So why there is a negative sign? This is an important question, right? Because as I told you, these two forces that are acting on these two balls will be same. Okay, the magnitude of the forces will be same, but the line of action or the direction of the two forces will be different. Hence, in order to distinguish between them, we have put a negative sign, okay, before on the RHS, right? So this is just illustrating that the magnitude of the two forces are equal, but the direction of two forces are not same. They are opposite to each other. Okay. So now from this Newton's third law, we will derive the equation of linear momentum, right? So for FAB, right, based on the above discussion, right, FAB, like from the Newton's second law, okay, we can write it as M times A, okay, M into MA into, okay, final velocity of body A and will be VA, right? And the initial velocity of body A will be UA, right? And of course, we would be dividing by time because we are finding out force. So, okay. So basically, if you find any difficulty in understanding this equation, right, it is like you can just simply start from this fundamental equation as read. Okay. So what I have done is that I have written this A as VA minus UA by T because acceleration is nothing. It is just the rate of change of momentum, right? It is the acceleration is defined as the rate of change of velocity with respect to time. So what I have done that I have substituted the value of acceleration equal to VA minus UA by T, where VA is the final velocity, okay, initial final velocity of body A, and UA is the initial velocity of body A. Okay, so this force is nothing. It is just used to find out the force exerted by the body A on body B at the point of collision, right? Similarly, for condition 2, FBA, okay, so in this case, we will be taking the mass of body B, right? Okay, so here it will be VB, that is the final velocity of the ball after collision, right? And VB and the initial velocity of body B, that is UB. Okay, just a second, let me write it clearly. So it will be UB, right? And we will divide it by time, right? So basically what we have done is that like based on the above principle from the Newton's third law, right? Because at the point of collision, as I told you, the force exerted by body A on body B will be equal to the force exerted by body A on body B. But the line of action of two forces will be different, or the direction of the two forces will be different, right? Not the line of action, the direction of the two forces will be different. The line of action is, of course, like it is a difficult term to understand. So you can just understand that the force exerted by the body A on body B will be equal to the force exerted by body B on body A, and the magnitude will be same, but the point but the direction will be different. Okay, so now before, like few minutes ago, we at the point of collision we discussed it, right? FAB equal to minus of FBA, right? I just draw a diagram and illustrated it, like, okay. So now what we will do is like we have this two equations, right? So we will just substitute the terms here. Okay. So, so basically what this equation is telling us that this VA minus UA by T is nothing. It is just the rate of change of velocity with respect to time for body A, because body A will be exerting force on body B in the first condition. And this FBA is nothing. It is just representing this term. VB minus UB by T is nothing. It is just representing the change of acceleration, right? The rate of change of velocity with respect to time. Okay, and of course that will give us acceleration of body B. Okay. So what is VA? It is the initial final velocity of body A. What is UA? It is the initial velocity of body A. What is VB? Okay. After the collision. So, okay. After the collision, this body B, this body of mass MB will acquire a velocity VB. Okay. And this body MA will acquire a velocity VA. Okay. So now what we will do is that we will equate both these equations together. Okay. So now if we equate both the terms together, like simply we would just substitute these value in this equation 3. Okay. So now if we substitute these equation, okay, equation 1 and 2 and 3. So basically we would be obtaining a term like MA UA plus MB UB equal to MA VA plus MB U. Just a second. So after solving, we will observe that MAVA plus MB V3. Okay. So we will obtain this equation if we substitute the given values in equation, if we substitute equation 1 and 2 in equation 3, we would be obtaining this result that is drawn in the box. So basically what this equation is telling us that the rate of change of momentum, okay, the sum of rate of change of momentum of two bodies before collision is equal to the sum of rate of change of momentum of the two bodies after collision, right? But for this conditions to hold true, there are two exceptions, right? Two conditions needs to be fulfilled. The first condition is that the mass of the body should remain constant, right? It should not vary, right? And in the second case, this equation will only be valid if there is no net external force acting on the body, right? Because if there is net external force acting on the body will attain some then in this case, this equation will not hold true. Okay. So this, once again, I will just give you a brief description. So this equation is explaining us that the sum of rate of change of momentum of the two bodies before collision will be equal to the sum of rate of change of momentum of the two bodies after collision, provided the mass of the body should remain constant, and also the mass of the body should remain constant. Also, there should be no net external force acting on the body, right? If these two conditions are not fulfilled, then we cannot use this equation. Please keep a like a lot of students get confused related to this, but one should keep in mind that we can only and only use this equation if the mass of the body is constant, okay? Or in other words, like if there is no net external force acting on the body, only then this equation can be applied, okay? So basically what we did is that I will just give you a brief description once again. There is, before collision, there were two bodies. The mass of one which was MA, the other was at rest, body MB. Okay, the initial velocity of body A was UA, and of course, his initial velocity of body B was 0 because it has at rest. And for this condition, we considered that the velocity of body A will be greater than the velocity of B. Okay, so we can consider it at rest, or we can also assume that the body B is also moving with some velocity UB, right? But the velocity acquired by the body A will be much greater than the velocity of body B, because it has to collide, right? Until unless this condition is fulfilled, that the body will not collide with each other. So for this to happen, the velocity of body A has to be more than the body B, right? So basically, at the point of collision, I told you that the force exerted by the body A or body B will be equal to the force exerted by body B or body A, but the direction of these two forces will be opposite to each other, right? And at the point of collision, and after the collision, the body A will acquire the final velocity VA, and the body B will acquire the final velocity VB. So what we did is that we wrote two equations, right, based on the Newton's second law, right? FAB will be represented by M times A VA minus UA by T, okay, and FBA will be represented by MB VB minus UB by T, right? So basically now we will equate both the terms with the help of the Newton's third law, right? And on equating equation 1 and 2 and 3, we obtain the equation given in the box, right? So basically this equation is telling us nothing. It is telling us that if the mass of the body is constant and there is no net external force acting on the body, then the sum of momentum of the body before collision, sum of the momentum of the two bodies before collision will be equal to the sum of momentum of the two bodies after collision, right? This is nothing. This is just a illustration. This is just a derivation. This is just a mathematical formulation of this conservation of linear momentum, right? Equation, right? So this is nothing. This is just a representation of conservation of linear momentum, right? Okay. So this was all about the concept of conservation of linear momentum. And in the last segment, now let us deal with the concept of deal with some numerical problem, right? So here you can see that there is a question, right? We have to choose. This is a multiple choice question, of course, and only one answer will be correct in such cases, as we are aware. Okay, so this question is a previous year question that is asked in NTSC examination. Okay, it is a good question. So this is the reason I have taken this. Okay, so if you read through the question, it is saying that an object of mass m moving along a straight line with a velocity u collides with a heavier mass m and gets embedded into it. If the compound system of mass m plus m keeps moving in the same direction, then which of the given option is true? Okay, so as we can see in the options, like we will go by the options, right? It is best to go by the option. Like it is saying the kinetic energy before and after collision will be same. No, it will not be same. Like if we can also eliminate it from the options as well, right? The kinetic energy of the collision is okay. So now let us deal with this. Let us deal with this question, right? So if we apply momentum conservation principle, right? There is a body of mass m, okay, that is moving in a straight line, and it is given that its velocity is u, right? And then it's collide with the heavier body of mass m, right, and gets embedded into this. Okay, so now if I use conservation momentum principle, can I write this as, see, the equation of linear momentum is given by, just a second, it is given by pi equal to pf, right? So the initial momentum is given by m times u, right? And the final momentum after the body gets embedded into the system, there will be a combined, right? So can I write this as m plus capital M, where m is the mass of object and m is the mass, capital M is the mass of heavier mass into v, right? What is v? V is nothing but the final velocity of an object after object got embedded into the system of masses, right? So we have to assume this, right? This is not provided in the question. We have to assume it as v, right? So since initially a object of mass m was moving along a straight line with velocity u, so the initial momentum is given by m times u. But as soon as the body get embedded into the system, the combined mass will be m plus m into v, right? So from here, we can find out the final velocity of an object after it is getting embedded into the system. So the value will be m into u divided by m plus m, right? Since we have to find the change in the kinetic energy, right? So in order to find the change in the kinetic energy, why did we use this momentum conservation principle? Because we have to find the change in kinetic energy, right? So in order to find the change in kinetic energy, we need final velocity. In the question, the initial velocity of object of mass m is given, but as soon as it gets embedded into the system, that's the combined mass m plus m, we have to find the velocity for that. So we assumed initially that the initial velocity is v, right? So now if we have to find the change in kinetic energy, like delta k, okay, so the final kinetic energy, okay, if we want to find the loss in kinetic energy, the initial kinetic energy we can represent it by half m u square, right? And in case of second case, when the body gets embedded, we can write it by m plus m times into v, right? So I hope you understand what was the reason of finding this V, because like until unless we find this V, we cannot find the net change in kinetic energy, because we know that the object of mass is traveling with a mass object of small mass m that is traveling along a straight line with velocity u. But as soon as it get embedded into the system, we don't know the final velocity. Hence, we use momentum conservation principle to find out the final velocity. And now, since we have obtained the final velocity, we can find the net change in kinetic energy, right? So what we will do is that we half m v square. So we will substitute the above equation. Okay, the equation that is given in the box, let it be equation number 1. Okay, we will substitute the term in the second equation. Okay, so if we substitute the values, we have m plus m capital M into m into u by m plus m into v square, right? So if we simplify the terms, right, if we do the calculation, so we would be obtaining option. The final answer for this question will be, the final answer for this question will be half m into u square divided by m plus m. Okay. Okay. Now, so now let us match with the option. So in this case, as you can see that the correct option, the correct answer to this question is option 4, right? There will be loss of kinetic energy equal to half times this. So basically the same term, we have also obtained this, right? So this will be the correct option. So basically what we did in this question, like we use momentum conservation principle to find out the final velocity as soon as the body get embedded into the compound system, right? We were provided with the initial velocity, but we were not provided with the final velocity, right? In order to find the final velocity, we use momentum conservation principle, right? And in order to find the net change in the kinetic energy, like we have to find the loss, right? The loss in kinetic energy. So in order to find the loss of kinetic energy, we have to be like, we should have the final velocity with us. So what I did that, I used this equation, right, of v in the second equation, and then I simply simplified. Okay, so like by this way, on simplifying the above equation, if you simplify it, you will get option 4 as correct, right? So this is a very good question. It was asked in one of the NTSC examination. Like this topic of linear momentum, it is of utmost importance. It is asked in many Olympiads question, NTSC examinations as well as this concept you would also be learning in your higher grades as well, right? So this was all about this question, right? So now we will take another question to understand the concept of linear momentum, right? So you can read the question. A man weighing 60 kg runs along the rail with a velocity of 18 km/h and jumps into a car of mass 1 quintal standing on the rails. Calculate the velocity with which the car will start traveling along the rails, right? So we know that the momentum conservation principle is given by Pi equal to Pf, right? So the momentum before collision, right, will be equal to momentum after collision, provided the mass of the body remain constant and there is no net external force acting on the body, right? So can I write this equation as m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2, right? So now we have to be careful with the values that we are substituting, right? So in this question, m1 is 60, right? 60 kg, that is evident. And the velocity u1 will be 18 km/h, right? So we have in meter per second. If we convert that, it will be 5 meter per second, right? So we know what is m1, we know what is u1, right? And okay, and now if I want to find M2, right? M2 is given in the question as 1 quintal. Okay, so 1 quintal is equals to 100 kg, right? We know this. But it is, since it is written on the question that it is standing on the rails, right? So the value of U2 will be equal to 0. Why? Because it is at rest, right? Because it is mentioned in the question that it is standing on the rails, right? So we have covered all the terms on the LHS, right? Okay. Now in the question it says calculate the velocity with which the car will start traveling along the rails, right? So we don't know the value of V1, we don't know the value of V2, right? But from the above observation, we can definitely conclude that for this condition, V1 will be equal to V, and we can represent it by a single term, that is V, just for the sake of our simplicity, right? We would substitute this, right? There is no harm in like substituting. So now we have all the terms with us, right? We have all the terms with us. We can substitute them and like we can calculate, right? So the whole point of why this value of V1 and V2 was equal to V, like because at the point of collision, right, the body will possess a single velocity only, right? A man weighing 60 kg runs along the rails with a velocity of 18 and jumps into the car of mass 1 quintal standing on the rails. Okay, so in the after the like at the point after the collision, or not exactly collision, in the final condition, once the man has jumped into the car, the value of V1 and V2 will be same, right? It, like I hope it can be easily understood from the given condition, right? So what we will do is that we will simply substitute the value. The value of mass is 60, the value of U1 is 5, the value of M2 is 100, and the value of U2 is 0. Why? Because initially the car was standing on the rails at the position of rest. So since the body was initially at the position of rest, the value of UT is considered as U, right? So now, since I told you that V1 and V2 will be same, right? The final velocity or the initial velocity, the final initial velocity of body 1 and the final velocity of body 2 will be same, and that will be given as V. So the mass will get added up, right? So the mass will be M1 plus M2 if we take V as common, because the velocity will be same. Okay. So if you substitute the values, right? So it will be 60 into 5, right? This will become 0 only, right? So, and M1 plus M2 will be 60 plus 100 into V, right? So in the question, it was saying that calculate the velocity with which the car will start traveling along the rails. Calculate 3. Okay, so in order to find the velocity, what we did that we considered the condition that the V1 will be equal to V2, right? And we took it equivalent to a single term, that is V. Okay, and now we can easily find out the value of V. So if we solve this equation, right, we will get the value of velocity at 1.875 meter per second, right? If we do the calculation. Okay, so we will get the answer as 1.875 meter per second, right? So basically, this was all about the concept of conservation of linear momentum, right? Initially, we started with the concept of momentum, right? We correlated the two terms, mass and velocity, and how it is important in finding out the value of momentum, right? We used the momentum principle, right, to derive the equation of Newton's second law. Okay, and from Newton's second law, we deduce this to Newton's first law, right? So from this initial condition, we came to know that all these terms are closely interrelated to each other, right? From the momentum principle, we can obtain the Newton's second law, and from the Newton's second law, we can easily obtain the Newton's first law, right? And then in the second case, we discuss about the derivation or the mathematical formulation of the conservation of linear momentum, right? Here we assume the case of ideal collision. Okay, the body initially were traveling with velocity u and ub respectively, and their masses was ma and mb. right? And at the point of collision, the force that is exerted by the body A and body B and the force exerted by body B on A will be equal in magnitude, but the direction will be different, right? It will be opposite to each other. And after the point of collision, they will attain the final velocity v and vb respectively. And of course, their masses will remain same, right? And I told you one of the most important consideration that we take while finding out the conservation of momentum in the conservation of momentum principle is that the mass of the body should remain constant, right? And also there should be no net external force acting on the body, right? So like if these two conditions are fulfilled, then we can say that the law of conservation holds true, right? Then in the last segment, we solved few numerical problems, like based on the conservation of linear momentum, right? This was one of the good problems that we discussed. Like it has been asked in many competitive Olympiads as well. So like in this through this question, we learned like why do we need like how can we use the conservation of linear momentum in the real life, right? And we discussed one more question related to this linear conservation of linear momentum. So this was all about the topic of conservation of linear momentum. I hope uh, you have easily understood whatever I taught. Right. In the next lecture, we would be starting with the Newton's third law. Okay. We would be dealing with few live illustration and numerical problems as well. Right. I hope like this session was interactive. I hope I was able to clear all your doubts. Right. So looking forward to the next session. Like I would advise you to go through some previous year questions, right? I would advise you to go through previous year question and revise the topic again. Meanwhile, thank you so much. We will meet in other session.